Hello and welcome to this presentation. Today we will be discussing our senior design project, which is designing an experiment around the educational particle image velocimetry setup for the University of Central Florida. My name is Daniel Dyson. I am majoring in aerospace engineering, and I am the senior design project lead and the simulations team lead.
Hello, my name is Yvonne Zhang, and my major is mechanical engineering, and I am a member of the experiment team.
Hi, I'm James Henderson. I'm the experiment team lead, and I've been on the simulation team as well.
Hello, my name is Mohammed Ibrahim. I'm an aerospace engineering student, and I'm a member of the experiments team.
Hello, my name is Shana Rodriguez. I'm a mechanical engineering student, and I'm on the simulations team.
For this senior design project, our objectives were to design comparable and repeatable experiments using particle image velocimetry, or PIV. We were to design experiments and to also create simulations using computational fluid dynamics, or CFD software. We would also go on to compose a lab manual for future undergraduate students to employ while they perform the experiments and simulations in their future lab courses. This manual would allow them to properly run the experiments, the simulations, and collect all the necessary data for post-processing and comparison. It is our hopes that future students will be more exposed to fundamental topics in fluid mechanics, experimental design, and CFD.
There are currently very few opportunities for undergraduate engineering students to gain practical experience using systems which measure the physical world. This project gives students a more well-rounded educational experience when applying for engineering jobs. Additionally, this PIV system can be used for other PIV lab research opportunities on campus. Since it's water-based, it allows for low-speed, high-viscosity investigation of specific profiles.
Particle image velocimetry is an optical method to visualize flow in a fluid. The PIV system works by capturing photos in quick succession of a fluid such as water doped with small reflective pellets. A thin sheet of light illuminates the pellets within a two-dimensional cross-section of the fluid. In the accompanying software, the distance the pellets travel are tracked over time, allowing for the calculation of their average velocity in that section of the flow. The results show a vector map of the fluid velocities for the two-dimensional cross-section.
There are two major components to this project, the experiment and the simulation. The experiment part of the project includes 5 physical tank systems and a lab manual for students to follow along. The tank system includes a camera, a pump, a geometry which will be subjected to the flow, and the Dantec Dynamic Studio software, which interpolates velocity within the flow. The accompanying lab handout provides theory and context for the experiment, guides students through the lab procedure, and asks thought-provoking questions about the integrity of the experimentation. As for the simulation part of the project produced an ANSYS computational fluid dynamic ideal simulation of flow over a cylinder so that students may interpret and validate their experiment results within the context of fluid dynamics.
Fill the water tank. While the tank is being filled with water, connect the software dongles and camera to the computer and load the Dynamic Studio software. Mix 2 scoops of the seeding particles with 100 milliliters of water and 2 drops of dish soap. Add the mixture to the tank. Turn on the pump and the light sheet. Enter acquisition mode on the Dynamic Studio software. Adjust the focus and aperture of the camera to capture a particle density of approximately 15. Capture a single image to specify the scale factor. Adjust the sampling rate to around 130 Hz and input the number of images desired. Acquire the data and save it to the computer. Right-click the data for analysis options. Finally, view the results.
Extensive tests were completed to make sure that the experiment results are both reproducible and significant. It is important that the experiment is reproducible because 5 PIV tank system will be run by students in the lab, and having similar results with other students will help to convince students of the integrity of their experiment. Significant experiment results mean that the flow profile captured by the PIV system is as expected based on the ideal simulated results. Other than that, our senior design group have also designed a prototype support system that will allow the testing of flow over different geometries in the future, such as airfoil. The design will be shown as a CAD model and it will be easily reproducible. As for the project test plan, a good test would be to hand out lab manuals to some undergrads to make sure that they can follow along with the experiment. Input from these test experiments will ideally help us trim the lab manual down to the most important points, as well as phrase it in a way that will be easily understood. We will also time the experiment to make sure it is within our time limit for a lab session.
Our senior design team decided to use a variety of different tools to help collaborate and perform all of the necessary tasks. For example, we used Discord, which is a popular tool, and this allowed us to communicate effectively and efficiently via either text or voice channels. We also used a tool called Trello, which allowed us to organize our tasks using sticky notes in a cloud-based software. We also used Google Drive, which allowed us to organize our documents and reports for the senior design project. And it also allowed us to collaborate on those documents in real time without having to be in person.
Dr. Mazumdar was helpful for guiding the framework in which we approached this project. He helped us bridge the gap between theory and reality in our problem-solving methods, reeling us back in from our ideas which were too big, and helped us figure out how close our simulation should match the experiment. Additionally, the previous senior design team recorded help sessions with Dantec representatives, which helped us to troubleshoot hardware and software issues.
One major challenge that our senior design team faced was creating a CFD model that we believe students could gain a fundamental understanding of fluid mechanics from. For example, we initially considered modeling flow over a sphere, but we didn't know what the best direction was for creating that CFD model. Therefore, we made sure to perform a literature review and read over published experimental results and simulations for flow over a sphere. As it turns out, flow over a sphere is very complex and is out of scope for our project because we were limited to modeling a two-dimensional domain. However, flow behind a sphere is actually three-dimensional, and it would not show important characteristics such as a vortex street. A vortex street is a series of vortices that are being shed from the surface of the cylinder. And this is an important fundamental topic that is often discussed in fluid mechanics courses. On the left here, we can see an example contour plot of the velocity over a sphere. Flow enters the domain from the left and exits to the right, but we do not see a vortex street downstream of the sphere. Therefore, we needed to switch our scope of the project to considering flow over a cylinder. As you can see in this contour map on the right, we have flow over a cylinder where flow enters from the left and exits to the right. And in this case, we do see a vortex street. Therefore, we could create appropriate boundary conditions, appropriate viscous models to model the flow, and a proper domain to simulate the flow in.
One of the biggest challenges that we have faced by the experiment team is reducing the required time for both the students and the TA to set up and operate the lab within the given time frame. The way we did this was defining a clear method for filling and draining the tanks, which is much more efficient than the current method that we were given. We also established support systems which are able to interchange various objects quickly while also optimizing the software setup, run, and export time.
Since this project was a continuation of a previous team's work, it was satisfying to finish putting the puzzle pieces together left by them. Additionally, as undergrads, we wanted to produce a lab that we would have wanted to complete and that we would have found interesting.
One of the most important lessons that we have learned is that experimental data will never exactly reflect the simulation results, as a simulation produces an ideal representation of what our experimental data should produce. With ANSYS, parameters can be established in order to simulate the actual conditions of the tank. However, the backflow from the tank in real time will actually skew the data from the ideal simulation. Now, our motivation for continuing to focus on this project and solve these issues is that CFD and PIV both work hand in hand with each other. They contribute to the development of phenomenal new aircraft, rockets, motorized vehicles, or fluid systems in general. Motivation for us to stay focused was to perfectly reflect experimentation with simulation and vice versa. This is in order to fully understand and implement CFD, ANSYS, and PIV techniques into our future careers. Implementing new concepts with CFD and PIV, we can significantly reduce the time needed for innovating the future of efficient, affordable, and energy conservative designs wherever we apply them. There's a lot of uses for PIV and CFD as well. In order to develop new combustion engines, for example, the amount of time that this would take without any computer-aided modeling or real-time experimentation with vector mapping would be significantly more than what we are able to do now. What would take a few months for us may have been taken years back in the day.